All the forces that we encounter every day, whether we're shooting hoops, sending a rocket into space, or putting a magnet on our refrigerator, can be reduced to a crucial quartet: gravity, the weak force, electromagnetism, and the strong force. Everything that occurs in the cosmos is controlled by these forces. The four primary natural forces. Hello everyone, welcome to AWZ. Don't forget to subscribe our channel. Enjoy. Gravity. Gravity, which can be observed in the dropping of a rock from a bridge, planets orbiting stars, or the moon's influence on ocean tides, is the attraction between two objects that have mass or energy. The most obvious and well-known of the fundamental forces is arguably gravity, but it is also proven to be one of the most difficult to explain. The concept of gravity was first put out by Isaac Newton, who was allegedly inspired by an apple falling from a tree. He defined gravity as a real-world force that draws two objects together. Centuries later, Albert Einstein proposed that gravity is not an attraction or a force in his theory of general relativity. It results from objects bending spacetime, not the other way around. Similar to how a massive ball in the center of a sheet affects that material, distorting it and causing other, smaller items on the sheet to fall toward the middle, a large object has an effect on spacetime. Even though gravity is responsible for holding solar systems, planets, stars, and even galaxies together, it is really the least powerful of the four fundamental forces, especially at the molecular and atomic scales. Consider this: how difficult is it to pick up a ball off the ground? The gravity of the entire Earth is being resisted by all of those actions. Additionally, compared to the other fundamental forces, gravity has almost no influence at the molecular and atomic levels. It's incredible to believe that such a little magnet can overcome the gravitational pull of the entire planet. Of the so-called basic forces of physics, gravity is the weakest. Additionally, it is insignificant in compared to the electromagnetic force that holds the fridge magnet in place. When you stop to think about it, this makes perfect sense. Other forces are far more powerful than Earth's gravity, such as the strong nuclear force found in the atoms of the magnet. Additionally, it is powerless against the atom's weak nuclear forces, which cause radioactive decay. Earth is not a perfectly round object. It also has several mountains and deep gorges, which are lumps and bumps. Additionally, there are regional variations in the composition of the Earth. The combination of various rock types, mineral concentrations, and topography results in pockets with varied average densities all over the place. This has an immediate impact on gravity throughout the Earth's surface. This is rather simple to measure, and organizations like NASA have actually used spacecraft to map this effect. They were able to gauge the relative pull of the Earth's gravity as they circled the globe by using a pair of cooperative satellites. The weak force. Particle decay is caused by the weak force, often known as the weak nuclear interaction. Here, a subatomic particle is literally transformed from one type to another. So if a neutrino wanders close to a neutron, the neutron may become a proton while the neutrino transforms into an electron. The exchange of force-carrying particles known as bosons serves as the basis for how physicists explain this interaction. The strong force, electromagnetic force, and weak force are all produced by particular types of bosons. The W and Z bosons are the charged particles that make up the bosons in the weak force. These bosons can be exchanged between subatomic particles like protons, neutrons, and electrons when they are within 10 to 18 meters, or 0.1% of a proton's diameter, of one another. As a result, according to the hyperphysics website of Georgia State University, subatomic particles transform into new particles. The nuclear fusion reactions that fuel the sun and provide the energy required by the majority of living forms on Earth depend on the weak force. Additionally, it explains how archaeologists can use carbon-14 to date old bone, wood, and other artifacts that were once living things. Nitrogen-14, which contains 7 protons and 7 neutrons, is created when one of the 8 neutrons in carbon-14 decays into a proton. Carbon-14 has 6 protons and 8 neutrons. Because of the predictable rate of this degradation, scientists may estimate the age of these artifacts. Electromagnetic force. Between charged particles, such as negatively charged electrons and positively charged protons, the electromagnetic force, also known as the Lorentz force, operates. Like charges repel one another, whereas opposite charges attract. The force increases with increasing charge. Additionally, this force can be perceived from infinity of distances, just as gravity, albeit the force would be very, very small at that distance. The electromagnetic force, as its name suggests, is composed of 2 components, the electric force and the magnetic force. These forces were initially thought of by physicists as distinct from one another, but researchers eventually discovered that they are actually 2 parts of one force. Whether charged particles are moving or not, the electric component works between them, forming a field through which the charges can interact. But once in motion, those charged particles start to exhibit the magnetic force, the second element. As they move, the particles surround themselves with a magnetic field. As a result, a wire becomes magnetic when electrons rush across it to, say, turn on your TV, charge your phone, or charge your computer. Charged particles exchange massless, force-carrying bosons termed photons, which are also the particle constituents of light, to transmit electromagnetic forces. However, the force-carrying photons that switch between charged particles are a distinct type of photon. Although they are technically the same particles as the real and detectable form, they are virtual and undetectable, according to research from the University of Tennessee, Knoxville. Friction, elasticity, the normal force, and the force binding solids together in a specific shape are some of the most often encountered phenomena. These phenomena are all caused by the electromagnetic force. Even Superman experiences drag when flying because of it. It also affects birds, planes, and other flying objects. Charged or neutralized particles interacting with one another can cause these effects. For instance, the normal force that prevents a book from falling through a table is caused by the attraction between the electrons in the table's atoms and the electrons in the book's atoms. Powerful nuclear force. The strongest of the 4 fundamental forces of nature is the strong nuclear force, often known as the strong nuclear interaction. According to the Hyperphysics website, it is 6,000 trillion, that's 39 zeros after 6, times greater than the force of gravity. And the reason for that is that it joins the basic building blocks of matter to create bigger particles. It holds the quarks that make up protons and neutrons together, and a portion of the strong force also maintains the bond between the protons and neutrons in the nucleus of an atom. The strong force only acts when subatomic particles are extremely close to one another, similar to how the weak force works. They must be a distance of between 10 and 15 meters, or roughly a proton's diameter, apart. Contrary to the other fundamental forces, the strong force is peculiar in that it becomes weaker as subatomic particles grow closer to one another. According to Fermilab, it is strongest when the particles are separated from one another the most. The strong force is transmitted between quarks by massless charged bosons known as gluons, which also serve as the glue that holds them together once they are in proximity. The residual strong force, a little portion of the strong force, interacts with protons and neutrons. Because of their comparable charges, protons in the nucleus resist one another, but the residual strong force can override this attraction, keeping the particles bonded in the atom's nucleus. Nature as a whole. Whether the 4 fundamental forces are actually expressions of just one supreme force of the universe remains an open subject. If that's the case, each of them ought to be able to combine with the others, and there's proof that they can. However, physicists have had some difficulty fusing the microscopic and macrocosmic worlds. Gravitation predominates at vast scales, particularly astronomical scales, and is best characterized by Einstein's theory of general relativity. The natural world is best described by quantum mechanics, opens in new tab, at molecular, atomic, and subatomic scales. And nobody has successfully combined the 2 worlds to date. This is all for today. Don't forget to like the video and subscribe our channel. Stay tuned with AWZ.